Okay, settle down, settle down. Okay, welcome to the lecture of the elementary principles of the chemical processes. So today, as usual, we are going to, let's have a recap about what we learned last week. Last week, we start to know that how to measure the pressure and the temperature, right? I hope you still remember. So we start to know that what is the fluid pressure and then what is hydrostatic head. And then we also know that the relationship between atmospheric pressure, absolute pressure, and gauge pressure. Do you know, anybody want to tell me the relationship with these three pressures? Anybody want to tell me? Early bird, 0.5. Early bird, 0.5. What's the relationship between atmospheric pressure, absolute pressure, and the gauge pressure? So it's a kind of, anybody want to tell me? Last week, yes. Gauge pressure, right? Thank you. Very good, very good. Good. So you need to know this, and because we have a gauge, okay? Especially Bourdon gauge, remember? Bourdon gauge is for you to measure the pressure. So you need to know if the indicator tell you one, what is that? Is that absolute pressure or gauge pressure? And which is important because if you don't know, you cannot do the calculation right? Okay, you cannot tell people, or you cannot tell technician this is what's the pressure at this moment in a reactor. Okay, for example, right? So and you need to know that how to measure the pressure, right? We introduced Bourdon gauge. That's very important. I hope you should remember. That will be also in your midterm exam paper. And you also know that there's another pressure which measurement which is called transducer, pressure transducer. And that's very good but expensive, and we don't have time to introduce that to you. So you can check the information about the transducer in the internet if you want to. Okay, and then last is the temperature. You know the definition of temperature, right? Kelvin, Fahrenheit, and the Celsius, and the relationship between the Celsius and the Fahrenheit. Okay, and there's an equation related to Fahrenheit and the Celsius. And I also tell you the quick way to convert Fahrenheit and Celsius, or Celsius to the Fahrenheit, right? Remember? Okay, and then also we introduce you a measurement of the temperature that will call thermocouple. It's not thermometer, it's thermocouple, right? Thermocouple. So today we start from the thermocouple. I still have some of the information for you, and I hope you still remember. This is called thermocouple, right? So I hope you still remember this. The thermocouple is an electrical device consisting of two different conductors forming electrical junctions. So this is in the tip. There's two wires. And two wires get together and produce different voltage because of different temperature. So that's why we call the thermocouple produce a temperature-dependent voltage as a result of the thermoelectrical effect. And then this voltage can be interpreted to measure the temperature. That's why I need you to tell me in your midterm exam. Okay? And let me know you understand what's the meaning of the thermocouple. So this is the K type. There are many types because you have different alloys, and you put different alloy wires together. You produce different voltages. So one of the important type is called K type. That's what we use very often. The K type is the most common general purpose of thermocouple, with a sensitivity of approximately 41 microvolt per Celsius. So if we increase 1 Celsius, you increase 41 microvolt. So as you know, that you can calculate what's the microvolt increase related to the temperature. Okay, and this is a very good thermocouple because you can measure a wide range of the temperature from minus 22,000 Celsius to plus 1,350 Celsius. Very good. And so this including two parts. The first part is the this one, chromium. Chromium is that 90% nickel and 10% chromium. And aluminum is 95% nickel and magnesium 2%, aluminum 2%, and silicon 1%. So this is the one thermocouple, the tip, the top, or we call the probe, or the top of the thermocouple. So that's what I want to show you here, and I hope it's easier. So this is the, I think I have shown you this before, right? Last week. So this is the x-axis is the temperature, y-axis is the voltage. So related to this temperature, you can have temperature related to the voltage. Right. So it's going to be the end of this chapter. So you know, when we talk about temperature, if you have this, remember this is the protein, right? Protein, and these molecules vibrate because if you increase temperature, this vibration is getting more severe, right? So so if you make the temperature become 0 Kelvin, and you will be all the molecules or all the atoms will freeze. It won't move. So how can we make it become 0 Kelvin, or how can we make the temperature going down and down? So this is one of the most important, very famous experiment is that there's 3 scientists in the United States. They use 6 laser beam to focus on one single atom. And then this we call laser cooling. So if this atom doesn't move, that means the temperature in this point is very, very low. Okay, how low? So this is what we call laser cooling or Doppler cooling. So they use 6 laser beams. So the temperature can go down to 10 to minus 6 Kelvin. It's not 0, but it's cold enough. It's 10 to minus 6 Kelvin. So very, very low. So is this the world record now? No. They got Nobel Prize. That's 3 scientists got Nobel Prize because of this experiment. And it's 10 to minus 6 Kelvin. But now the technology improved. So now we can go to 10 to minus 12 Kelvin. It's not reached to 0, but it's very, very close already. Okay? Very, very close. So these 3 gentlemen got the Nobel Prize because of this experiment. So they, you know, there's no absolutely 0 in the world, but you can make it very, very small. Okay? So because of this chapter we talk about fluid. Have you heard about superfluid or supersolid? This is a very interesting thing. You know, if we talk about superfluid, that means that every time when we talk about fluid, we talk about viscosity. If like air or water, you always talk about viscosity, 粘度. But superfluid, there's no viscosity. It's 0 viscosity. It's a very strange phenomenon in the world. So I don't have time to talk about this to you. Right. That's all for the things in chapter 3. And now let's move to the chapter 4. So the chapter 4, which is one of the most important chapter in this book. Okay, in this book. Well, which in this course, I should say. Okay, and you should study well and to know well in the chapter 4. So the chapter 4 is the fundamental of the material balance. So basically we are talking about material balance, energy balance, and momentum balance. But the concept of the balance are all the same. So if you know how to do material balance, then you will know how to do energy balance. And you will know how to do momentum balance. Okay? So material balance or mass balance is the first step to go through from material balance to the energy balance and to the momentum balance. So, and you need to know the laws of the conservation of mass. Of course, there's the conservation of the mass, right? And mass balance and or material balance. Okay, let's go back to the process again. The process is very important because you are a chemical engineer. You are all chemical engineers, and then you need to know all the processes. So let's see the classification of processes. So the A classification is that you can classify the processes into 3. So one is called batch process. The second one is continuous process. The third one is not batch or not continuous. That's why we call semi-batch. So batch normally is for the for the process which conduct with a small quantity of the materials. Okay, so but for the continuous process is always for the large production. I just in the chapter 1 we use penicillin as an example. Remember, for you to know what is batch, what is continuous process. Okay, and the number 2 classification of the process is what we call steady state process or transient process. So what is transient? Transient, it can be you can use unsteady state. Sorry, what happened? Okay, so here I'm going to introduce this one by one to you. So what is batch process? The batch process is that first you add, this is a container, you add reactants in this container, and then you do the process. It can be a chemical reaction or it can be a physical process, okay? Physical mixture or something. And third one is remove. You got a product, so you remove. So it's kind of batch. As you know, you cannot make a very big tank of the batch because this is especially for small quantity. Like when you are at home, you want to cook, for example, you want to cook noodles, right? Soup noodle. And then you put water, you put noodles, you put vegetable, you put egg into the container, and you cook. And you finish, and you take it out, you put it to the bowl, and you start to eat. So this is kind of process, right? And this is what we call batch process. But that's for you. But if you want to serve 1,000 people, you cannot cook like this, right? You need to make it quick, right? So you need to find out another way, which is continuous process. So the definition of the batch process, this is important, is no mass crosses the system's boundaries. This is what we call system boundary, right? No mass crosses the system boundaries between the time feed is charged and the time the product is removed. So once you feed the product, the feed into this, and you started to do the process, and after that you remove it. So this is the definition of the batch process. For example, this is one of the examples is you want to make a cup of coffee with milk and sugar, right? So you put the black coffee first, and you put the milk, and you put the sugar, and you stir it. And you can have a, what's that called? Latte, right? Or cappuccino, whatever. Okay, so what is the continuous process? If we use this as an example, that means we have a feed A into this reactor or this container. We have a feed B into this container. We stir it. But at the same time, we have a pipe here. The product come out continuously. So we keep on feeding A and B into this reactor or mixer, for example. And we have C continuous come out. Okay? So the rate in will be equal to rate out. This is what we call steady state. Steady state. Steady state is that the level of this liquid or fluid is it won't increase or it won't decrease if the rate in equal to the rate out, right? Okay. So the definition of the continuous process is that the inputs and the outputs flow continuously throughout the duration of the process. So if we have a boundary here, this is the boundary, right? And then input continuously go into this reactor or go into this container, and output continuously come out to this container. Okay, this is what we call continuous process. So this is the comparison of a batch process and continuous process. Remember? I think this is, you have mix and then finish, go to next step, and then go to next step and you get a products. But here is that you have a feed, you have reactants go into this reactor and it change, you see that from the red ball to the gray ball, it change continuously and change and then come out to become the products. Okay, so this is a kind of comparison. So what is semi-batch? The semi-batch can be two kind of cases. For example, if you produce the gas come out in a batch process, and you need to release gas. Why? Because if you don't release gas, the pressure will increase here, and then if you don't release, it will explode, right? Okay, so it cause danger. Or A in and B in, and then we don't release at the same time, but for a period of time we release. Okay, so any process is neither batch nor continuous. We call semi-batch. Easy, right? Right. I want to make an example of you. Do you know this? Taiyaki. Do you know what taiyaki? Taiyaki is, right? Taiyaki is. This is called imakawa yaki. It's what we call hongdobing, right? There are two types of process. One is batch process, one is continuous process. Okay, so if you go to the street, you see this, right? You see this. This is batch or this is continuous. This is a batch process because you make this in the same place and you take it out. Okay? So then what is combustion? Just for fun. Okay, and how about another classification, which is steady state and transient state. Steady state is that the definition of steady state is the variable do not change with the time except minor fluctuation. So the temperature, pressure, and volume doesn't change with the time. But here you see the time except minor fluctuation. It can be increase a little bit, decrease a little bit, but we regard this doesn't change. So this is what we call steady state. So the process is in the steady state and normally it's continuous process. Because what? Because if you have fit into here, in this point, in this point, in this point, in this point, the temperature different. But in this point, the temperature, pressure doesn't change. Although this point and this point, the temperature and pressure might different, right? Might be different, or the composition might be different. Okay, so this is what we call steady state. Steady state. How about transient unsteady state? Transient unsteady state is if you have a tank, you put the reactants into here, and the temperature change, and the concentration change. For example, if you boil a pot of water and you put a dumpling into this pot. A dumpling. Do you know what is dumpling? Dumplings. What is dumplings? 水饺, right? Dumplings. If the dumpling will drop, if you put a dumpling into this water, the temperature dropped and increased, right? Because you want to cook the dumplings. And the dumpling itself, the temperature increased. Okay? So the temperature changed. So this is called transient state or unsteady state. Okay? So it applies to the batch process and continuous process. Startup. Startup means what? Startup means that when you start to put the reactor or start to put the things start in the first, for example, 10 minutes, it hasn't reached steady state. It might be unsteady state first for the first 10 minutes, and after it becomes steady state. Okay, so you have a continuous process. You have continuous products. Okay, this is definition of classification. Another classification of a process, which is steady state and unsteady state, or we call transient state. Right. So next is the balances, the general balances equation. This is also very easy. So a process, as we know that this is a process unit, it can be a chemical reactor or it can be a physical mixer, right? So suppose methane is a component of both the input and output streams of a continuous process unit. This is a continuous process, so it can be a pipe, right? It can be a pipe. So methane was fed into this unit, and then it will come out. So methane into, as you can see, this continuous process, so I have a time, methane, the mass divided by time, so this is flow rate. Okay, so mass, remember this M, it represents mass, right? This is input, and there's over dot here represent what? Flow rate. Okay, and then I have output. So I have input and output of methane. If something happens, if the input doesn't equal to output of methane, what happened? What's going on? You might think, well, Professor, the methane go into this reactor and methane has a chemical reaction with something, and methane reduced. Right? The amount of methane reduced. Okay, case 1. Case 2 is, well, the methane go into this reactor and then methane increased. It can be possible, right? So why? Why? Let's think of this question systematically. First one is that methane has been consumed as a reactant, right? Consumed, that means the output will be less, okay, or generated as a product with the unit. So methane reduced, we call consumption. Methane increase, we call generation. It can be generated, right? For example, inside you have carbon and hydrogen, it becomes methane, for example. Okay, and as case 2, methane is accumulating in the unit. Okay, so methane absorbed, stay in this reactor or stay in this mixer. It doesn't come out. So methane accumulated in the units, possibly absorbing on the wall. So we call accumulation. Methane stay inside. It's not consumed, it's not generated. Okay, case 2. Case 3 is that methane come out, not in this direction. Methane was leaked because this container is not good. So methane leak from this container. Okay, and case 2 might be, well, the measurement is not correct. So you have flow rate meter. That if we want to measure the flow rate, what's the device we use? Anybody want to tell me? What's the device you use to measure the flow rate? Measure the flow rate. What kind of device? Especially volumetric flow rate. Anybody? Raise your hand. 0.5. Yes. Parameter. I don't know. It's called rotameter. Rotameter. Okay. Okay. Thank you. Thank you. You got 0.5. It's called rotameter. Or you can answer me in Chinese. It's called 浮子流量计. Okay. 浮子流量计. Okay. So you know the rotameter need to be calibrated. Remember we have an example. Okay. But if you don't calibrate the rotameter, the reading might be wrong. So you have wrong reading. It's not good, right? So you collect all the possibilities. For example, there are four possibilities of the input doesn't equal to output. For the case 1 and case 2, we discuss later. For case 3, the measurement leak from the unit. You can do the check. You can do the fix. You can fix the reactor, or you can fix the container, right? So you can remove this possibility. Okay, so the measurements are wrong, so the rotameter doesn't function well. So you can do the calibration before you do it. You try to before you do the experiment again. So you remove this possibility. So the only thing left is that it can be consumed inside the reactor. It can be generated inside the reactor, or it can be accumulated in the reactor, in the container, or in the unit. So, as we know, the conservation of a mass. So the mass need to be conserved. So we have 5 terms in this place, and we need to make it as an equation. For example, input, output, methane generated, methane was consumed, or methane accumulated in the reactor or container. So you have 5 terms here. And you need to make a balance because the conservation of the mass, right? Okay? So how can you make an equation here? Input, output, and it can be generated inside. It can be consumed inside. It can be accumulated inside the reactor, the unit. Okay, so let's make an equation here. Input, originally if we don't have generation, consumption, accumulation, input equal to output. That's for sure, right? But if you have these 3 terms, how can you put these 3 terms into this reaction? So input will plus generation or minus generation to become output, plus or minus? Plus, right? Because if you generate methane here, input plus generation will equal to output, right? Increased. How about consumption? Plus or minus? Minus, right? Minus. How about accumulation? Plus or minus? Minus. Okay, so you have this equation. Ladies and gentlemen, you need to remember this for your entire life as a chemical engineer. Okay, this is easy. Very easy. Well, you might say, well, Professor, this doesn't look like the same as what I read in the textbook. It doesn't perform like this. Don't worry, I will show you later. So this equation this is what we call general balance equation. This can be used if you change to mass to become energy, the same. If you change to mass to become momentum, that will be the same. Okay? So this is universal equation. This is what we call general balance equation. So you say, Professor, this equation is not correct. It's not what I saw in the textbook. The textbook show you this. You just remove these two terms from left to the right, from the right to the left, from left to the right. This is what you saw in the textbook. Anyway, it tells you the same thing. So in your midterm exam, I think if I ask you to write down general balance equation, please write this for me. Okay? You might get 2 points. And then this will be M equals input plus generation minus output minus consumption. Okay, equal to accumulation. Okay? Am I right? Yes. Just different. Anyway. So input is what? Input is enters through the system boundaries, right? This is input. The output is the generation is produced within the system. And then, the output is that lives through the system boundaries. This system boundary, right? And the consumption is consumed within the system. Accumulation is what? Build up within the system. Build up. Okay? So this is easy. So I have a very simple example for you to understand. For example, Minxiong City. This is a city. Okay? This is a city. Every year, Minxiong Town, I should say, Minxiong Town, there are 50,000 people move in, like you, right? Your first year, you move into the Minxiong Town. So, for example, there are 50,000 people moved into this city. Okay? And there are 75,000 people move out from this city, like you. When you graduate from Zhongzheng University, and you might don't want to come here anymore, right? You move out. Okay? So this input, this is output. And then there are 22,000 baby, okay, infant, a baby born in this town, newborn baby. Okay? There are 19,000 people die, consume, right? Generation consume, die. So is this town, the population of this town growing or losing people? Okay, this is easy. So you just use general balance equation as a kind of example, the Minxiong town. Okay, you need to know is this increasing or losing people in this town, or how many of them? Okay, so you need to know the accumulation. Please do this by yourself. Easy. Right. So I think let's refresh ourselves before we move to the next topic. So it's time for playing Kahoot now. 都是因为卡户都会过，都会答得好啊，不会就被当的。通常看到都是期中考、期末考很不好，然后呢，卡户也没怎么在玩，这不是没怎么玩，考完都没有答对哦。你们最后决战点哦，很多都是卡户哦。好，所以呢，卡户不难，对不对？哦 ，Right. So once we do general balance equation, there are two types. Again, the one is batch process. One is continuous process. Okay. So assume when we think of this case, you have method input and method output. So this is called differential balance. Differential balance is related with time. Remember, you divide it by time. You can count as 1 second, 1 minute, 1 hour, 1 day. Or normally we don't count 1 day, it's too long. So normally count by time. Okay? So you apply to the continuous process. And then that's another one, integral balances. Integral balances, you only think of the initial state and the final state. right? So it's regardless of the time. It doesn't mean it can be 1 day, 1 hour, 1 year. You just count the initial state and final state. Okay, 1 year later, final state, or 1 hour later, final state. Okay, and this, of course, this applied to batch processes. So this is also important, the rules to simplify the material balance equation. So this is general balance equation. It applies to the mass, energy, and momentum. And how can we simplify this equation? So if we want to count the mass in total, so mass in equal to total mass in equal to total mass out. Okay, so what we think is that there's no generational consumption because we follow the conservation of mass. So there's no, unless it's nuclear reaction, you will lose some masses. Unless there's a nuclear reaction. Otherwise, chemical reaction doesn't lose any masses. Okay, so the conservation of mass should be equal to, if there's no generation, there's no consumption. So you can remove generation, the terms of the generation and consumption. Okay, for the total mass balance. And the other case is if this is not a chemical reactive species. For example, nitrogen. There's no it's very difficult to have a chemical reaction with nitrogen. So nitrogen will be input and output. It can be regarded as a carrier gas. So if the species is not a chemical reaction species, so there's no generation and there's no consumption. So again, you can remove the terms of generation and consumption. So input minus output equal to accumulation. Okay, the case 3 is if this system is in a steady state system. That means variables is not going to change. Okay, so steady state normally we talk about, you remember, steady state process normally is continuous process. If this is continuous process, there's no accumulation. Why? If there's continuous process and accumulation is not a steady state. If you accumulate some species inside this and increase, the accumulation will increase and increase. So this won't cause steady state. So accumulation we will remove the term of accumulation. So what I want to tell you is, if this is not a chemical reaction process, and this is a continuous process, and also this is a continuous process, so you can remove generation, consumption, and accumulation. So as a result, the general balance equation will become input equal to output. So you remove generation and consumption and accumulation. Okay? Right, so I have some example to show you later. So balances on continuous steady state processes without chemical reaction. So that will be all purely input equal to output. So accumulation, so this is a steady state, right? So as we know that accumulation will equal to 0. So continuous steady state is that accumulation equal to 0. That means what? This term is always continuous state. This term has a certain people, which is there's no losing people, there's no increase. The people doesn't increase or we don't lose any people. So you will stay in a kind of certain population with a minor fluctuation. Remember? So accumulation equal to 0. So you will become input plus generation equal to output plus consumption. And if there's non-reactive species and total mass balance, now generation and consumption will be equal to 0. And as a result, this equation, general balance equation will become very simple. become input equal to output. You might say, well, Professor, this is so easy. Yes, this is easy. But we have some complicated example for you to digest. Okay, so this is example 4.2-2, material balances on a continuous distillation process. Okay, distillation, do you remember, do you know what is distillation? 蒸馏, right? 蒸馏. And now AI is very popular. Distillation. AI, 像 Gemini、OpenAI 他们也用 distillation 这个字，还记得吗？他们蒸馏一些 data 出来。Okay, so, you know, in the chemistry class in your high school, you use this kind of distillation column, right? Remember? And then you separate A and B because of different temperature, different boiling temperature. Okay, but this is chemistry class, but you are a chemical engineer. This is a chemical engineering process. So we need to know how to do this in a huge reactor, huge unit, and continuous process. This is not a continuous process. This is a batch process, right? Okay, but anyway, I don't introduce distillation, continuous distillation process for you at this moment. But what I want to tell you is, you just regard continuous distillation process as a kind of unit here, and then distillation process is a non-reactive process. So consumption, generation, you can remove consumption and generation terms, right? And this is a continuous process, so you need to be steady state. Okay? Regardless of the startup time for the continuous process, so this is steady state. So you remove the terms of the generation, consumption, and accumulation. So as a result, input equal to output. Okay? So, I don't have time to read the text with you, but what I want to say is that the benzene was fed into this distillation column 500 kilograms per hour. Okay? And then toluene was fed 500 kilograms per hour to this distillation. So this is a mixture. You know, benzene and toluene can be mixed together very well, but you want to separate these two things. Okay? And because of boiling differences of boiling temperature, the one product will be on the top stream, one product will be the bottom stream. Which one will be on the top stream? Which one? Okay, you don't know, but you can find. You might know that. Well, the boiling temperature, lower boiling temperature will be on the top. So the boiling temperature, if you have a weak boiling temperature, that means what? The interaction of the molecules, benzene to benzene, will be weaker than the toluene to the toluene. Okay? So as a result, benzene will be on the top because benzene has a lower boiling temperature, boiling point. And toluene will be on the bottom. However, this is a kind of simple process. So you won't have 100% benzene on the top stream. You don't have 100% of the toluene in the bottom stream. You have a small mixture. So the textbook tell you that the benzene on the top stream will be 450 per kilogram per hour, and the toluene will be 475 kilogram per hour in the bottom stream. So I want you to know that how many toluenes on the top stream, how many benzene on the bottom stream, in the bottom stream. Can you tell me this? Yes, very easy, right? Because benzene input equal to benzene output. So 500 equal to 450 plus X, for example, here. And benzene, toluene, 500 equal to what? Input equal to output. Toluene, Y plus what? 475. So that's easy. But the concept is input equal to output, because this is a continuous, non-reactive process. Okay, so input equal to the output. Okay. So please, I think you can practice this by yourself, easy. So the section 4.2 integral balances on the batch processes. So before, this is a continuous process. So how can we do the calculation of the batch process? So this is batch process. This is a Haber process. We use this as an example. For example, nitrogen plus hydrogen become ammonia under the pressure, very high pressure of 200 atm at a very high temperature of 500 Celsius, and also with a catalyst. Remember catalyst? Catalyst doesn't involve any chemical reactions, but it can reduce the additivity energy. So you can accelerate, it can reduce the condition, it can make the condition become lower to make this reaction happen. Okay? So you have initial state and a final state. So this is a batch process. And you go into do input equal to output. Or you have a generation and consumption, right? So assume the amount of the ammonium in the very beginning is n sub 0 mole. The time is t sub 0, which is 0. And then for a period of time, the amount of ammonia will be NFF, stand for final. Okay? Time T sub F, F stand for final. So you use general balance equation. And because this involves chemical reaction, so you cannot remove generation and consumption term here. Okay? So, but you don't have input. And you don't have output. So you just count the initial stage and the state and final state. Okay? You don't have consumption. Okay? Because this is a irreversible process. Okay, so there's no consumption of ammonia. So you don't have consumption. So as a result, the generation will equal to the accumulation. Okay? So there's an example in the textbook, please. You can read it by yourself. So mass balances of any species in a batch process. This is a tip for you to express. That will be expression of for the batch process of initial input plus generation equal to final output plus consumption. Okay, it can be nitrogen, it can be hydrogen, it can be ammonium, because ammonium have no initial input, right? Okay, for the expression for the continuous process, steady state, that will be input. Instead of initial input, that will be input, right? Instead of final output, that will be output. That's it. So this is another example. This is the batch process. The balance on a batch mixing process is that you have mixture of the methanol plus water, which is 40 weight percent, 60 weight percent, and you have 200 grams into and put it into this container. Another one is methane 70%, water 30%. You have 150 grams put into this container. And the question is that you need to find out what's the total mass and what's the composition of the methanol and water in this container or in this beaker. Anyway, this is very easy. I don't want to waste your time. So the point is that for a chemical engineer or in our course, we don't draw something like this. We want to draw a flow chart like this. I will tell you this in detail, maybe next lecture or the lecture after next lecture. Okay, so we use simple like this. This is a process, and this is a mixer or mixing. So this information will be here, and this information will be here. And this information will be here. So this is a mixer. So this is the representation of this story. Okay? So you need to realize that flow chart is very important for you to understand or for you to analyze all the problems or all the questions. Right, I don't want to waste your time, so please do this by yourself. Oh, by the way, this is it's important to write something like this, right? Dimensional equation. Okay, integer balances on a batch, semi-batch or continuous process is also easy. So I want to let's do this quick. So batch process is regardless of the time, right? So you have initial stage, and final state, but so this applies to the batch process. However, if you have semi-batch or continuous process, it's related with time. Okay. So you use differential balances. Differential balance is easy divided by time, but if you times time, you convert the time, it becomes integral balances. This is not difficult at all, so easy. Okay, so another example is integral balances on a semi-batch process. We use hexane as an example. This is hexane. Hexane is a liquid. So you have air going to this hexane liquid, and air was 0.1 kilomoles per minute. You might say, well, Professor, why we don't use gram? Remember this? Because we don't use gram to represent gas. We use mole to represent gas. Okay, liquid, if we use liquid, we use gram. Okay, so also the mass balance. So why we want to do that? Why we want to introduce air into this liquid and let the liquid come out? What is this for? Because when you come out, you have air and what? Hexane. Right? So if I take hexane away, I put water here. Can you tell me why is this? Can anybody tell me why is this? If you put air, if I replace water to the hexane here, and I put the air into this container and make the air and water come out, what is this? What is this? Humidifier, right? Humidifier, 增湿器, humidifier. Right? In winter, if you go to Japan, Japan is very, very dry in winter. So you'll get statics, even in the room. So you need humidifier, 增湿器, to make the room with waters. Otherwise, you'll get statics. When I was in Japan, I get statics all the time because the room is too dry, the outside is too dry. When I was in the United States, the summer is very dry. It's not winter. Summer is very dry. So you need to have a humidifier, okay, 增湿器, so you don't get statics, 静电, okay? Anyway, so we want to introduce some of the hexane out, mixed with gas, mixed with air. So that's why we need to have this process. Okay? So as we know, this exercise tells us that we want to design to come out with 10% hexane and 90% air. So you have 100% air input, and the output will be 10% hexane and 90% air. And then we want to know what is the flow rate of this. Can you tell me? Can you tell me? Yes, right? That's very easy. Okay. Input air input equal to air output. So you can get how many output of this. Okay, this is question 1. Why? Because air and hexane it doesn't react. Hexane doesn't react with the air. So the reaction is not involve any reaction. So there's no generation and there's no terms of the generation and consumption. Okay, and also this is a continuous process. So accumulation equal to 0. That means air as in subsolute in hexane. Okay, so there is no accumulation of air in this container. So this accumulation equal to 0. So as a result, input equal to output. So that's very easy. So can you find out n for me? Yes. And can you find out if I want to get 10 cubic meter hexane, how long does it take? Because you have, this is 1 minute you got this, right? 1 minute you got this one, and if I want to get 10 cubic meter hexane, how long does it take? If you know the flow rate. Okay? So, please, this is volume, right? You need to know the density. Right, so again, I don't want to waste your time, so please practice this by yourself. So as a result, you know that you need this much time to get 10 cubic meter hexane out. Right, so hexane is a kind of gasoline, and it's a kind of non-polar solvent. Okay, we commonly use this as a solvent for it's kind of non-polar solvent. Right, and Haber process. Remember Haber? Haber is nitrogen plus hydrogen equal to ammonium. Okay, this is irreversible. And Haber, he got Nobel Prize because of this process. Why? Because ammonium can become a fertilizer. Fertilizer can make food. So, before the First World War, he saved a lot of people's life because of this invention. Okay, 肥料. So he fed a lot of people to prevent hunger. Okay, he got Nobel Prize. Okay, he's a great man. On the other hand, he's a killer because he got an invention of the toxic gas, which is chlorine toxic gas. So in the First World War, he used chlorine as a toxic gas to kill a lot of people. And his wife killed suicide because of this. Okay? And he's a great man. He killed a lot of people. He saved a lot of people from hunger. Okay, he saved a lot of people's life. Anyway, and he died in the Second World War because he's Jewish. I don't know exactly he's a Jewish because you know, some kind of tragic. Anyway, you can find out his story in the internet. Okay, so this is a 4.2 summary. You know the continuous process, batch process, and semi-batch process. Right, okay, seems we still have time. Should I go ahead? Right, I think I better stop here before we move to the section 4.3.